Hey guys, we are going to start our new unit on logarithms today. I really enjoy the logarithms unit and I've noticed that most of my students usually do as well. And you'll notice it's not quite as difficult as the unit we just got done with, so that is nice too. But logarithms are actually really applicable in day-to-day stuff. Seems like a weird name and that we wouldn't use them, but they actually are used in lots of ways. So logarithms are opposites of exponentials. Remember, everything in math always has an opposite. So when you have an exponential function, this is a graph that starts off really slow and then spikes. So in the news, we've been seeing a lot of exponential stuff with the coronavirus, starting off slow and then all of a sudden spiking with cases. So logarithms are the opposite of that. It's where you start really steep and then you level off slowly. So that's why we can use logarithms so much, is because exponential things show up all the time in the natural world, and so do logarithms because they are inverses of each other. So today we're going to learn how to rewrite equations in exponential form and then rewrite them in log form. So we're going to learn that you can go back and forth between these two formats. And then we're going to learn how to evaluate log expressions not using a calculator. So let's just look at these graphs really quick for a second though. Again, an exponential function is where you have some base that's a number. So like 2 to the power of x, 5 to the power of x. A really common one is the number e to the power of x. We'll get to that one later. These again start off slow and then they spike really quickly. So one thing about exponential functions is they will always have a point going through 0, 1 on the y-axis. And that's because if x is 0, any number to the power of 0 equals 1. So it doesn't matter what the base is. If I'm going to put it to a power of 0, it's going to equal 1. So that's a point that you can just memorize to help you graph exponential functions. And then a second point we can use to help us graph is 1 comma b. So at point 1, if I go over 1, it will always be whatever the base is high. So like on this one, it's going through 3. That would mean this equation would be 3 to the power of x. If it was 4 to the power of x, then this point would be going through 4. If it was 5 to the power of x, then this point would be going through 5. So that's another way you can help learn to graph it. But their domain and range, the domain is going from negative infinity to positive infinity, left to right. But then the range is going from 0 to infinity. So we do have that horizontal asymptote on the x-axis. So again, the y-intercept is at 0, 1. And then we have our end behavior, which we won't focus too much on. And logarithms are opposite of that. If I drew a diagonal line, y equals x, this is going to reflect over it. That's going to be the logarithm graph. So if I had a horizontal asymptote on this one, I am now going to have a vertical asymptote on the logarithm graph. So you'll notice the domain on this has to be positive. It's going from 0 to infinity because we do have that vertical asymptote. But then the range is now all y numbers. So we are going from negative infinity up to positive infinity. So they're opposites of each other. This domain becomes this range becomes this domain. And again, that's kind of one of the definitions of an inverse. Some points to help you graph on this one, really similar to over here, but instead of a point being at 0, 1, again, they're inverses, so we flip them. This one will be at 1, 0. And instead of being at 1 comma b, this one will be at b comma 1. So if we look at the actual equation for a log, we have the log with this little subscript right here. This is what we call the base of the log. So we use the letter b to represent it. Whatever this number is will be this x value for this point. So it looks like this one is over 3. So right now this graph would be a log base 3. If it was a log base 5, then this point would be over at 5, 1, and so on. So just kind of remember these are inverses of each other. So their points are opposites of each other. Their x's and y's flip. And if this has a horizontal asymptote, this has that vertical asymptote going down. So exponential and log functions are inverses of each other. Two of the most widely used or most common logarithms are the common log, which is just a log with a base of 10. And then because we use this base 10 so much, again, mathematicians are lazy. So instead of writing log base 10 over and over and over again, we just leave it off. So if you ever see a log without a base on it, you will just assume that it's a log base 10. Because again, we're just lazy. So, and then the other one that we use a lot is what we call the natural log. That's because it happens in nature quite a bit. It is the inverse of an exponential function, which is a base e. So if you have learned about the number e, it is a number, kind of like pi, that goes on forever and ever, doesn't end. And it happens in nature quite a bit. So we use that as the natural number. And so if I have a log base e, for some reason, instead of writing log base e, we just write ln. So that ln stands for the natural log of x, or whatever you're looking at. So it's kind of your intro into logarithms and exponentials. But today, one of the things we're going to talk about is going back and forth between log form and exponential form. And that also works with going back and forth if you have a natural log and an exponential with base e. So if we have a log, remember there's this little base subscript. We say log base b of x equals c. So that's how you would read it. If this is my logarithm, I can switch it into the exponential format by writing it like this. So whatever my base is going to stay the base in my exponential. But then this c that we're equal to over here becomes the exponent. And whatever x was inside the log is what it's going to be equal to. And so here's kind of my little visual trick. If I cover up the log with my finger, this looks like a number raised to an exponent, right? Just like this is a number raised to an exponent. So my little trick is if this is my base raised to this, the x and the c just switch places. And so that's how you go back and forth between them. So if I have b to the x, it's now going to be b to the power of c. So x and c just switch places. And then for natural log of x, remember natural log and e's go together. So if I'm going from a natural log, it's going to be a base e. And that's because the natural log is the same as log base e. We just don't write log base e, we write ln. So this e is going to be the base, and then the x and the c still switch places. So again, you can just think of it as being log base e of x. We just are lazy and write ln. So we're going to practice converting back and forth between those. So I have log base 4 of 64 is equal to 3, and they want us to write it in exponential form. So again, my little trick is if this is the base, I'm going to cover up the log. That's going to stay the base of my exponential, but then these two switch places. So 3 is going to become my exponent, and it will equal 64, which is true, right? 4 to the third power is equal to 64. 4 times 4 times 4. So that would just be your answer. So when they ask you to write in exponential form, you're just switching the format. You're not solving for anything. You're just going from one format to the other format. So same on this. If I cover up the log, 5 is my base for my exponential, but then -2 becomes the power, and then this is what it's equal to. And sometimes you'll see people have parentheses around that. It's just kind of a formatting preference. But that's true as well. If you remember your exponent properties, if I have an exponent that is negative, what that means is that we would put it in the denominator and then it turns positive. So 1 over 5 squared is 25, so we get 1 over 25. So that one's true. And then again, if you do it one more time, 65 is the base in the log. That's going to stay the base in our exponential, but then 0 becomes the power, and then it will equal 1, which again is true. Anything to the power of 0 is equal to 1. So let's try going the other direction now. So we're starting in exponential form, and let's write it into logarithmic form. So whatever the base is in your exponential is going to be the base in the log. So I'd have log base 3, and then the 4 and the 81 switch. So 81 comes in here. Again, you can put parentheses around it if you want, just a formatting preference. You don't have to. And then this 4 is what it's going to be equal to, and that would just be your answer. So we're just changing the format. On this one, we have a base 10. So you could write log base 10, but just know most people don't write the base 10 because we just use log alone. And that's because log base 10 is going to be the most common log that you use, so we just don't write it. So I don't necessarily need to write this in there. We would just put the 1 over 100 on the inside, and then it would equal -2. But again, it's like there's a base 10 there, we just don't write it. So let me block that out. So most commonly you would see this written like that without the 10 on there. And then on this one, 6 is our base, so I would get log base 6, and then 6 comes on the inside, and that will equal 1. And if you want to put parentheses around it, you can. So you might notice that these two numbers match. This will actually lead us into some properties that we get down here. If you ever have a log where the base and the inside number are the same, it will always equal 1, no matter what. So if this was like 7 and 7 or 8 and 8, if those two numbers match, it will always just equal 1. So basic properties of logarithms. I just talked about this one. That's the second one right here, that if the base and the number on the inside are the same, then it just equals 1. But the first one is if I have log of any base number, if the inside number is 1, it will always equal 0. So log base 10, log base 5, whatever that base is, if this number is a 1, it will always equal 0. And on the converse of that, if I'm doing the natural log, same thing. If I have a natural log of 1, it just equals 0. So here's the regular logs over here, and then the natural logs are in this column. So again, there's that one we talked about. Log base b of b is equal to 1. So if these match, it equals 1. And then for natural log of e, that will also equal 1. And so again, you can think of that as being a log base e of e. We just don't write log base e. We write ln. But if you write it out like that, it matches this format where these two are the same number. So it's going to equal 1. Another property is, let's say the base and the number on the inside match, but this number has an exponent. Think of these as canceling, but this exponent is going to come out. So whatever the exponent is, in this case it's c, that will be your answer. And same with the natural log. If I have a natural log of e, that c is just going to come out. And again, you can think of that as being a log base e of e to the power of c. So think of these as canceling with each other. That c, oh, I wrote a 1, I don't know why I wrote a 1, will come out and be your answer. Okay, and then last property, let's say I have an exponential raised to a logarithm. When you have this happen, exponentials and logarithms are opposites, they're inverses. So they cancel out with each other. So this base, as long as it matches the base number inside this log, these two numbers do need to be the same. They cancel with each other, and whatever x is going to come out. And we're going to use that property a lot now, and then also when you get into calculus, you will be using this to help solve things quite a bit as well. And that's because if I want to get rid of a log or get rid of an exponential, we always use the opposite thing. So same if I am using natural logs, remember e's and natural logs go together. So if I have a base e raised to a natural log, they are opposites, so they cancel, and that x will just come out and be your answer. So that's how we would get x isolated or get it alone when solving, is by doing the opposite exponential or the opposite logarithm. So those are the properties we're looking at. If you want to, you can pause the video and write these down so you have them. Sorry, I don't have a packet to give you guys right now, but you can just write those down really quick. But let's look at some of these properties. Here I have log 10 of -4, but notice there's not a base written. If that happens, remember it is a base 10. So if I have that base 10 written, which property would match this one? I have a base with the same number to an exponent. So this would be property number 3. So my answer would just be whatever that exponent is, it would just equal -4. So I'll just say this one is property number 3. Part B, I have e raised to the natural log of 6. That is going to be property number 4. Since we're using the natural logs over here, it'll be this one. If I have e to the natural log, think of these as canceling with each other, and that 6 will just be your answer. So this is property number 4. Okay, on this one I have log base 3 of 1. If I look at my list of properties, that's going to be this one right here. It doesn't matter what the base number is, but if this number is a 1, then it will always just equal 0, no matter what. So this is property number 1. And then the last one, I see that these two numbers match. So this is going to be property number 2. If these two numbers match, it just equals 1 every time. So this is property number 2. So when we are getting later into the unit, when we are solving different aspects of logarithms and exponentials, these properties will show up. So that's why you want to know them, because it can help you simplify while you're solving.